The most interesting star, I think, the star that could be shocking in our sky is this one, Betelgeuse or Betelgeuse.
They are among the biggest explosions of radio energy in the entire universe.
Sending ominous signals through the cosmos, the red giant star called Betelgeuse hovered on the edge of our galaxy. Astronomers have discovered something very unsettling about this cosmic ethereal body. Brian Cox, a renowned astrophysicist, issues a serious caution as questions arise about whether this could bring about a disastrous supernova explosion that might alter the night sky forever. Join us as we explore the imminent explosion of Betelgeuse, as Brian Cox warns. Betelgeuse, one star in the universe, has recently captured the attention and concern of astronomers and the general public. This red supergiant star, of immense proportions and age, is called Betelgeuse and is visibly situated in the constellation Orion. Although this star's unique reddish hue and fluctuating brightness have sparked intrigue for a long time, recent developments have enhanced interest in this ethereal giant. This red supergiant is a cosmic giant, approximately 764 times bigger than our Sun. Its giant side is almost beyond the comprehension of humans. It is so huge that if it were to replace the Sun, its surface would extend beyond the orbits of Mars. It would engulf Mercury, Venus, Earth, and Mars in its stellar grip. This generous size is not merely physical, but also influences the star's life cycle. The red supergiant is in the twilight of its existence, a phase whereby a life spent fusing hydrogen into helium in its core is followed by expansion and cooling. Believed to be 8 to 8.5 million years old, the star is relatively young in human terms, although ancient in the context of cosmic lifetimes. Its current phase is the culmination of millions of years of stellar evolution, a period marked by dramatic alterations and procedures that have transformed it from a hot blue star to the red giant it presently is. The life cycle of stars such as Betelgeuse is a transformation story, driven by the relentless forces of nuclear fusion and gravity. Another peculiarity it currently possesses is its unique reddish hue. Compared to other stars like the Sun, its relatively cooler surface temperature results in its red color. The Sun's surface temperature is about 5,500 Kelvin, while Betelgeuse's surface temperature is roughly 3,500 Kelvin. Light emissions at wavelengths that give it a red appearance can be traced to this cooler temperature. Providing clues about the star's physical condition and the processes happening within its vast, gaseous expanse, the red color is more than a visual trait. The supergiant's historical color change adds to its uniqueness. According to ancient Roman and Chinese writings, Betelgeuse was yellow about 2,000 years ago. The first time the planet was tagged red was in the 9th century by Arabic scholars. The color shift is relevant because it serves as a window into the star's evolutionary path. An additional intriguing aspect is the fluctuating brightness of the celestial body. This implies that its light periodically waxes and wanes as a semi-regular variable star. And this luminous variability has also intrigued astronomers and skywatchers for centuries. Alongside a longer cycle of about 5 years, the star undergoes a 400-day cycle. Sir John Herschel documented these cycles as far back as 1836, and it could be earlier in Aboriginal oral traditions. The Great Dimming. The mysterious factor about the star, however, is its variable brightness and irregularity. Contrary to several stars that follow an expected pattern, the star sometimes deviates from its rhythmic dimming and brightening, hinting at complex and less understood processes happening within its giant form. A recent groundbreaking revelation known as the Great Dimming has captured the attention of astronomers and stargazers with an unexpected and dramatic change in its appearance. The red supergiant, one of the brightest stars in the night sky and a remarkable feature of the Orion constellation, began to dim mysteriously in late 2019. The dimming was so significant that the star started averaging a daily loss of 0.01 magnitudes in luminosity until it reached its lowest brightness in February 2020. Even in light-polluted areas, the star was usually visible to the naked eye, but it became so faint that the change was obvious to amateur observers. One of the issues surrounding the observation of the colossal star is the time paradox. The time paradox occurs when a star is viewed, and it is not seen in its current existent form, but as it existed in the past, due to the time it takes for light to travel to Earth. In that case, the Betelgeuse's light we perceive presently left the star almost 7 centuries ago, approximately 725 light-years away. Due to this time lag, predicting and monitoring abrupt changes in a star's behavior is challenging, as we are essentially looking into its past. In observing variations of the red supergiant, Hubble spectra were also utilized. Hubble spectra. Andrea Dupre, an associate director of the Center for Astrophysics at Harvard and Smithsonian, and her team closely monitored Betelgeuse's celestial drama display. As part of a 3-year study to monitor variations in Betelgeuse's outer atmosphere, they utilized Hubble to analyze the gigantic star. These observations were insightful in understanding the dynamics of a fluctuating star like Betelgeuse, which expands and contracts regularly, bringing about variations in brightness. The researchers probed the layers above the star's surface, which were heated partly by the star's violent convection cells, through Hubble's sensitivity to ultraviolet light. The Hubble spectra, taken at different points throughout 2019 and 2020, were subjected to further analysis that aided in measuring material movement in Betelgeuse's outer atmosphere. The spectra specifically focused on magnesium-2 lines, which indicate the star's atmospheric conditions. These observations showed material moving at about 200,000 miles per hour from the star's surface into its outer atmosphere. Eventually extending millions of miles from Betelgeuse, this hot and dense material served as the prototype for the dust cloud that led to the star's dimming. Dupree and her team estimated that about twice the usual amount of material from Betelgeuse's southern hemisphere was lost over the 3 months of the outburst. Like all stars, Betelgeuse continuously loses mass, although at a much greater rate than the Sun's. This mass loss was significant. Speculations were sparked among astronomers about whether the scale of this mass ejection and the subsequent dimming could be a precursor to a supernova explosion. Theories proposed to explain the sudden change. In a bid to explain the sudden change in the red supergiant, several theories have been proposed. A prominent theory suggests a phase in the supernova explosion process, a hypothesis that gained traction due to the common belief that Betelgeuse is close to the end of its life. Dust, possibly from the star itself, was obscuring our view, another popular theory implicated. Like other red supergiants, Betelgeuse is known to shed material, and the material was speculated to have the ability to form a dust cloud dense enough to dim the star's light from our view. The third explanation stated that changes in the visible surface layer, the star's photosphere, could affect its apparent brightness. Using several observational methods, in-depth analysis helped solve this mystery. A drop in Betelgeuse's effective temperature was indicated by spectroscopic studies, which suggested that the dimming could be traced to a large dark spot on the star's surface. Supported by the observation that Betelgeuse's temperature dropped by a minimum of 170 Kelvin around the dimming, this theory points to significant changes on its surface. The Hubble Space Telescope's observations revealed that the dimming of Betelgeuse was possibly caused by a significant ejection of hot material into space. The material formed a dust cloud, obscuring a portion of the star's surface and effectively reducing the amount of light reaching us from Betelgeuse. The dust cloud was speculated to have formed from superhot plasma, which erupted from a huge convection cell on the star's surface, after which it moved through its hot atmosphere to the colder outer layers. It formed dust grains as it cooled, creating a cloud that blocked light from about a quarter of the star's surface. Beginning in January 2019, Hubble's ultraviolet light spectroscopic observations were critical in merging the timeline leading up to Betelgeuse's darkening. Signs of dense, heated material were captured moving through the star's atmosphere in the months preceding the dimming. Many ground-based telescopes also noticed the star's brightness decreasing, especially in its southern hemisphere, in December 2019. Initially more luminous than the star's normal brightness, this material eventually formed a dark cloud as it moved outward and cooled. The hypothesis stated that this outflowing material and the resulting dark cloud caused the star's sudden dimming. The star expelled approximately 400 billion times the mass typically released in a standard coronal mass ejection. This expelled material, believed to weigh as much as the Moon, was relevant for Betelgeuse and our understanding of stellar mechanics. Traditional understanding suggests that red supergiants such as Betelgeuse shed mass at a relatively stable pace before the explosive end of their lives. However, the scale of this ejection challenges this notion, suggesting a more violent and likely unpredictable end-of-life phase for these stars. Recent studies theorize that the star could be preparing for its final supernova explosion within the next few millennia, indicating that it could be sooner than initially expected, possibly in merely a few decades. Bow shock. A bow shock is created when this colossal star hurls through space at approximately 67,000 miles per hour relative to its surrounding interstellar medium, similar to the wave formed by the bow of a moving ship. The phenomenon occurs as the star's outer layers interact with the interstellar gases and dust, providing an extraordinary testament to its dynamic nature and interaction with the universal environment. The study of this bow shock obtained information about the current state of Betelgeuse and contributed to our understanding of cosmic evolution and mass loss processes. Following the ejection event, the star's surface has been observed to cool and become less dense, leaving the star unstable for years. A connection between the star's convective activities, mass ejection, and subsequent pulsation mode switching was suggested by hydrodynamic simulations. This continuous instability triggers questions about the internal processes pushing these changes and how they might culminate. As observed, the star's mass loss rate is significantly higher than that of several other stars, inferring a complex interplay of internal forces. Partly responsible for this mass loss, the driven pulsation is limited by the stable energy dissipation through shock heating and mass ejection. Challenging astronomers to reconsider their models of cosmic evolution, such observations accentuate the dynamic and slightly unpredictable nature of Betelgeuse's life cycle. What a special red supergiant this star is. Although the timing of the supernova remains uncertain, the recent unprecedented mass ejection has undoubtedly shifted the conversation, hinting at a closer end than initially expected. This is controversial information. The supernova SN 2023 IXF. The supernova SN 2023 IXF is another universal event that captures the attention of astronomers and skywatchers alike, and it offers a clear comparative study. The galaxy Messier 101, informally known as the Pinwheel Galaxy, featured this spectacular explosion situated merely 21 million light-years away. SN 2023 IXF is not merely another supernova. Discovered in May 2023, it is the nearest one observed recently, providing a priceless close-up of a star's explosive finale. This rapidly brightening speck on the outskirts of Messier 101, using a modest 0.35-meter telescope, was first noticed by Koichi Itagaki, an amateur astronomer renowned for his supernova discoveries. SN 2023 IXF's behavior was meticulously documented in the tumultuous month following its discovery. Within 5 days, the supernova surged from relative obscurity to dazzling peak brightness, only to start a more gradual descent, dimming by 0.03 magnitudes daily. How rapid that dimming is. A surplus of bright emission lines was revealed by special analysis, evidence of the violent interaction between the expanding supernova shockwave and the gas surrounding the star. In addition to being a star ending its life, it was a massive star collapsing under its weight as its nuclear fuel was exhausted, and the outer layers rebounded off the dense core in a striking core collapse supernova. However, SN 2023 IXF is specifically intriguing because of the dense shell of gas that envelops it, which significantly affects the escape of the shock wave from the star's center. This dense circumstellar material could be explained in two possible scenarios. Either a strong, steady wind had been shedding material from the star before the explosion, or the star experienced random outbursts, hurling material into space. Either way, it is estimated that the star lost a solar mass of material in the last 1 to 2 years of its life, signifying that its final moments were not serene. The absence of serenity sends out another message. A focal point of study has been identifying the progenitor of SN 2023 IXF. Researchers have agreed that the likely candidate is a red supergiant through several methods and datasets. Astronomers can refine their models of stellar evolution and supernova mechanics by studying the details of SN 2023 IXF's explosion, including its progenitor's characteristics and the mechanisms leading up to its final detonation. Offering a clearer picture of what signs to look for and how to interpret the massive red giant's complex behaviors, these insights directly inform our understanding of Betelgeuse's current state and its potential path to supernova. Tohoku University in Japan conducted research that suggests Betelgeuse might presently be in the carbon-burning stage of its life, a phase that precedes the end of a star's life. Hideyuki Sayo, the leader of this study, posits that the star's core could collapse a few decades after the carbon is exhausted. On the other hand, researchers from Konkoly Observatory in Hungary believe that Betelgeuse is in an earlier helium-burning stage. Despite these contradictory views, there is a consensus that Betelgeuse is likely to be the next supernova in the Milky Way. But the occurrence of this event might take another 100,000 years. That's about 100 millennia years, a lot of time. Observations of supernovae have provided priceless insights into stellar deaths, according to history. Dating back to 185 CE, the earliest confirmed record of a supernova was observed as a bright star that faded from the sky in 8 months. Ever since, various significant supernovae have been recorded, including SN 1006, the brightest recorded star to ever appear in our night sky, visible across various parts of the world, and SN 1054, which resulted in the formation of the Crab Nebula and was visible in daylight for 23 days. Studied extensively by Johannes Kepler, the most recent supernova observed in the Milky Way was SN 16/4. However, the first supernova detected through neutrino emission and observed across every band of the electromagnetic spectrum, called supernova 1987A, was more recently observed in the Large Magellanic Cloud, within hours of its light reaching Earth. Detecting a supernova through neutrino emission is a leap. In developing successful models of supernova behavior and understanding their role in star formation, these observations have been crucial. Crab Nebula. The Crab Nebula is an expanding remnant of a star's supernova explosion. This violent event, which occurred almost 1,000 years ago in 1054 AD, was recorded by Japanese and Chinese astronomers and the Native Americans. Expanding since the star exploded, the glowing relic is now estimated to be 11 light-years in width. One of the largest images ever taken of a supernova remnant by the Space Telescope is the Hubble Mosaic. It is also the highest resolution image ever made of the entire Crab Nebula, which is located 6,500 light-years away. From 24 individual exposures taken with Hubble's Wide-Field Planetary Camera 2 in October 1999, January 2000, and December 2000, the composite was assembled. core collapse supernova. A type of explosion that takes place when massive stars exhaust their nuclear fuel and can no longer support their gravitational collapse is termed a core collapse supernova. It is one of the most energetic and cataclysmic universal events. It is also categorized as Betelgeuse's impending supernova. As much energy as our sun emits over its entire lifespan of billions of years in a matter of seconds will be released when Betelgeuse eventually goes supernova. The energy output from a supernova typically takes the form of electromagnetic radiation, including visible light, X-rays, and gamma rays. A spectacular light show in our night sky, nonetheless, would be the most immediate and visible effect of a Betelgeuse supernova. The explosion would briefly outshine the moon and would be visible during the day. One might imagine witnessing a second, incredibly bright sun appear for a few weeks or months when gazing up at the daytime sky. Captivating both astronomers and stargazers, the event would be breathtakingly celestial. However, its true significance depends on the scientific opportunities it presents, regardless of how fascinating the visual spectacle of a Betelgeuse supernova would be. Especially massive stars like Betelgeuse and supernovae are cosmic laboratories that offer invaluable insights into the integral workings of the universe. The opportunity to witness the final stages of stellar evolution up close would be one of the immediate benefits of observing a Betelgeuse supernova. Elements forged within their cores, including heavy elements like iron, are distributed into space when massive stars like Betelgeuse explode. For enriching the universe with the building blocks of planets, stars, and life itself, this process is responsible. Scientists can gain a deeper understanding of how stars evolve, fuse elements, and contribute to the formation of new celestial bodies by studying the spectroscopic signatures and the distribution of these elements in the aftermath of a supernova. For unraveling the history and composition of the universe, this knowledge is crucial. Subatomic particles called neutrinos are also emitted in the cosmos. Neutrinos. Alongside the dazzling visible light from a Betelgeuse supernova, the emission of neutrinos is equally intriguing. Neutrinos are subatomic particles that are notoriously difficult to detect because they rarely interact with matter. However, they are produced in vast quantities in the intense environment of a supernova. A unique window into the heart of a dying star is offered by these elusive neutrinos. Shedding light on the fundamental forces and particles at work during a supernova explosion, neutrinos can provide information about the core collapse process. A momentous scientific achievement would arise from detecting and analyzing these neutrinos, potentially unlocking secrets about the universe's most extreme environments. Dark energy. Dark energy is the enigmatic force, and the implications for our understanding of the universe's expansion could be impacted by the observation of a Betelgeuse supernova. In the late 1990s, observations of distant supernovae resulted in the discovery that the expansion of the universe is accelerating, not slowing down as initially speculated. Being relatively close in cosmic terms, the Betelgeuse supernova would provide a valuable data point for studying the expansion rate of the universe and the role of dark energy in driving it. Possibly revealing new mysteries about the fate and nature of the universe could aid in refining our understanding of these fundamental cosmological concepts. Furthermore, considering the vast distances that separate humanity from the red supergiant, the Betelgeuse supernova is unlikely to cause danger. For context, imagine that 1 light-year is approximately 5.88 trillion miles. In that case, at 725 light-years away, Betelgeuse is more than 4.267 trillion miles distant from our planet. With this enormous separation providing cosmic insulation to an extent, any direct physical harm to Earth from the explosion is highly unlikely. The thought of a light-year being that far is shocking. That distance is beyond imagination. What a magnanimous distance. It makes it easier to understand the statement, light years ahead of something else. Neutron stars. The observation of each new neutron star enables us to deduce the properties of neutron star matter with precision, and that is a mesmerizing sight to behold, research lead author Jonas Natala said in a statement. When stars with masses between 10 and 20 times the mass of the Sun run out of the fuel necessary for intrinsic nuclear fusion occurring in their cores, neutron stars are born. In turn, the outward energy that held the star stable for millions or billions of years against the inward pressure of its gravity has ceased. With gravity, a star's core begins to collapse. The outer material of the star where nuclear fusion occurs gets blown away in a massive supernova explosion as this happens. Condensed to a width of only 12 miles or 20 kilometers, the stellar core is left with a mass between 1 and 2 times that of the Sun. This massive reduction in the size of the neutron star creates matter that is so dense that just a sugar cube-sized block of it would weigh about 1 billion tons if brought to Earth. For context, that sugar cube weighs as much as 3,000 Empire State Buildings. Cold quark matter. Cold quark matter is devoid of protons and neutrons. Scientists can't visit neutron stars to get a sample of this material because the closest neutron star is about 400 light-years away. So the best alternative is to simulate the conditions beneath the star's surfaces using a powerful combination of real astronomical data and supercomputers. Bayesian inference matter, a type of statistical deduction that calculates the likelihood of different model parameters by making direct comparisons with observational data, was used in this new research. With this, the team determined the boundaries for neutron star matter, leading the crew to conclude the presence of cold quark matter to a high degree of probability. A state of matter that exists in neutron stars that is non-nuclear, in which quarks are allowed to exist, deconfined in protons, neutrons, and other particles, was also suggested by the mechanism. Aleksi Voron, a professor of theoretical physics at the University of Helsinki, said their constituent quarks and gluons are liberated from their typical color confinement instead and are allowed to move almost freely. A probability below 20% that matter within neutron stars experiences a rapid change of state from nuclear matter to quark matter is also suggested by the team's supercomputer simulations. Such a quick change in matter could destabilize neutron stars in a way that could make a tiny quark of matter collapse to birth a black hole, similar to water changing to ice. The existence of quark matter cores could be fully confirmed in the future, with some further analysis of the research offered as well. Determining the strength of the phase transition from nuclear matter to quark matter would be the key. With improved observational data, better models of neutron star cores will require a vast amount of computational power and time. A team member and a graduate student at the University of Helsinki said they had to use millions of CPU hours of supercomputer time to be able to compare their theoretical predictions to observations and to constrain the possibility of quark matter cores. Remnant. The shape of a remnant and the distribution of its elements can allow astronomers to create 3D simulations depicting how a supernova ejects its debris, how that debris interacts with the interstellar medium, and, ultimately, how it ends up in gas clouds that form the next generation of stars and planets. According to Anderson, this study is timely. Recent works have identified hundreds of possible supernova remnants that need to be confirmed. Finding the remnants isn't just an exercise in cataloging them. This discovery is yet another captivating one. Hopefully, these diligent scientists will make the most of this discovery, and the red supergiant will stay on track. In correspondence with the discovery of the cosmos, would you like to flaunt your up-to-date knowledge? Recently, our team unveiled the Cosmos Tough Phone Cases. Take advantage of this opportunity to grab this durable, long-lasting, and attractive phone case at a discounted rate. To place your order, simply click on the link available in the description. What do you think about the new information on Betelgeuse? Let us know your thoughts in the comments section below. Thank you for watching. Kindly like and subscribe to our channel for more thrilling videos like this.